It's physics X today.
Okay,
You're supposed
all right.
to know what's going on. You're not.
Okay, so I have like 8 pages of notes to get through today, so no questions, no clarifications, nothing. I help you not. No! No! If I drag your name out, I will ask you a question. You have 3 seconds to answer. You understand me? Got it. Let's go. No, I'm just kidding. I do have a lot to get through.
Do you have recording? Is it recording?
Yes, it's recording. Good Lord. Okay. So in special relativity, okay, so I'm gonna lay some stuff on you, which anyone who took GR is gonna be like, wow, why aren't you going slower with that? Why are you going so fast? Well, we're not gonna manipulate it the way that we did in general relativity, but we are gonna have to take into account various things. So I'm gonna cover some important aspects of special relativity that are quite a bit more sophisticated than what you've seen in your special relativity in the past. So first of all, in special relativity, we see many quantities with upper and lower indices. What is so funny? What is so funny? Okay, all right, fine. So I'm going to talk about, I'm going to break these down into 3 different categories. And hopefully this little summary will really drive the point home. And if you're not used to working with these, this might be all new and you might be like, la, 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 la. But if you've seen this, you're like, yeah, that's great. Okay, but it's kind of a good addressing of all of this index stuff. And sadly, I am going to be clear and consistent going forward, but a lot of books aren't. Okay? So, so first of all, one of the primary things that you encounter in special relativity is the idea of tensors. So, if you want to define a tensor with some words, the words you might say is a tensor is a multilinear map from the space of vectors and dual vectors into the reals. That's a technical definition. The more effective definition, which we used in GR, was?
A tensor is something that transforms like a tensor.
Well, why did you use tensor in the definition of tensor? That makes no damn sense, but that's exactly what I said in general relativity. If something transforms like a tensor, that's how you know it's a tensor. So the tensor is a transformation property of something. And so if you don't know if something's a tensor, you gotta look. Now, Sophia, how many tensors have you worked with throughout your education thus far?
None.
None. Okay, how many of you have worked with tensors? Okay, it's about half and half in the room, and that's standard, okay? Actually, to be completely honest with you, you've all worked with tensors. You just didn't know it. No one was brave enough to say, oh, that's a tensor, okay? So let me say a couple things about tensors, and we'll get by. So, first of all, our tensors will be PQ tensors, meaning that a PQ tensor has P upper indices, so P1, or I don't know, 1 dot 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 P, and then Q lower indices, 1 dot 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 Q, okay? And these don't have to be in a row, and these don't have to be in a row. They can be all mixed up and crazy. But that's what when I write a tensor and I label it with a set of parentheses and 2 numbers, that's just telling you how many high indices and how many low indices it has. The distinction between the high indices and the low indices is exactly the distinction that we talked about last time between a vector and a dual vector. Okay? A vector has an upper index and a dual vector has a lower index. So if I have a tensor that has, say, you know, here I'll give this an index structure that's concrete, like h, mu, nu, lambda, rho, sigma. Okay? What kind of tensor is that? Sophia, now you get a question. In terms of this notation.
I don't know.
Well, how many upper indices does it have?
3?
3. How many lower?
2.
So it's a
3, 2.
It's a 3-2. Yeah, it's that. I'm not asking the hard questions, trust me. Okay, so what kind of tensor is this? Anyone? It's a 1-0. What about this?
0-1.
0-1. Okay, that's all we're doing to label things. Okay. Now, Now, remember from last time that the difference here is that an upper index lies in a representation R of your transformation group, whereas a lower index lies in the dual representation. Okay? And just to be sure, when we write a V mu, we really mean the transpose of the R twiddle. Okay? Now, of course, R twiddle transpose R is an invariant, so that of course means that V mu is an invariant. Okay? And this largely just follows from the fact that we make the dual vector such that it transforms inversely to the vector so that their transformations cancel each other and the combination is invariant. Okay? And these are representations of SO1, 3 if we're talking about special relativity, which we are. Okay, now there's something nice you can do. You can contract tensors. So you can say, if I have a dual vector V mu, and I hit the 2, 0 tensor mu with it, okay, then you might notice something, and this is something which I swear you'll get so good at once you work with tensors that it'll be like nothing, but the first time you're working with it, it's intimidating. What kind of tensor is this?
Nu 0.
Say it again.
Nu 0.
Nu 0?
1, 0.
Did you say nu 0?
Yeah, 1, 0. Sorry.
Yeah, it's a 1, 0 tensor.
I'm telling you.
Now, it's got one lower index and two higher indices, so why isn't it a 2, 1 tensor? Somebody answer the question.
Well, it's because of that inner product, the product of the covariant functions.
Yeah, it's because there's an index that is repeated, therefore that index is summed over. So when you look at a tensor or a combination of tensors, the first thing you have to do is just ignore repeated indices because they get summed over and they are not part of the transformation rule. So if this thing were to be transformed, you'd really only have to worry about the transformation rule for the new index because the mu and the mu prime, or the mu and the mu here get inverse transformations, so they cancel. Okay. All right. Now, some tensors can be represented by matrices. So this is good word to Pat Cole. So for example, a vector we would normally do as a column vector. So we just put 4 things in there. A dual vector. Remember, this is the transpose of the dual representation, so we would always write that as a row vector. And then we could take a 2-index tensor with 2 upper indices. That, of course, would be a 16-component thing. Or we could take one of them up and one of them down, and that would be also a 16-component thing. Or we could take them both down. Okay? 2 important observations, which is why Pat Cole was incredibly wrong when he said, tensor, that's just a matrix. Okay? If I gave you the following matrix, and these were all values, and I said, what kind of tensor is that? Which one is it? You don't know. Okay? You have to label where the indices are on a tensor because they determine how the tensor transforms. This transforms with 2 vector indices. This transforms with 1 vector and 1 dual vector index, and this transforms with 2 dual vector indices. So this labeling with the up and down indices is incredibly important. But here's an even more important observation. Write that as a matrix.
you need a cube, three-dimensional dimensions to write it.
Write that as a matrix.
You need 4 dimensions to write it.
Okay, anyway, the point is the notion of a matrix is a 2 by 2 array. Something with 3 indices has got more dimensionality to it. And then, I mean, you can draw it as a cube, and then you can do cubic matrix multiplication, but don't do that. I'm going to give you methods to do this multiplication without having to use matrices. Okay? But there are situations where matrices are a useful way to manipulate these things. And last but not least, each upper index, of course, transforms like a vector. So if I have an upper index, then I have the upper index transformation rule. And if I have a lower index, I have the lower index transformation rule, where this is mu prime mu, and this is mu prime. Oh, sorry. Okay. Any questions about tensors in general? Really, you're going to write most of them as matrices or vectors, okay? Because we don't really get beyond the second rank tensor in this class. In general relativity, definitely do. But how they transform is an incredibly important part of the tensor story. Okay, second important ingredient in all this is the metric tensor. So as we talked about, the metric tensor is a tensor which carries a vector into a dual vector. Okay, remember the metric takes you from a representation into the dual representation in general. And since these vectors and dual vectors are elements of representations and dual representations, the metric carries us from a vector into its corresponding dual by applying the metric to the vector like this. Okay? The inverse metric does the opposite. So if I hit a dual vector with the inverse metric, then I get a vector out. So this is the inverse of this. So G mu nu is equal to G mu nu inverse in terms of its matrix representation. So this is obviously represented by a matrix, right? It's got 2 indices. So one index is your row, one index is your column. So too here. So we're just talking about the components of a matrix there. The metric is a true tensor, so it transforms as a true tensor should. So we've got mu prime mu and nu prime nu. Okay. Now, there's a couple more comments I made about the metric in here, which I'm not going to go through. But what is special about everything I've said so far is true for a metric in general. But in special relativity, if we choose the rectangular coordinates c, t, x, y, and z, the c is just there so that these all have the dimensions of distance. In this coordinate choice, then the metric takes this very special form, which we call eta mu nu, which is what I've been writing all along, -1, 1, 1, 1 down the diagonal. Okay? Hopefully it's clear to you that the metric would change if I instead used polar coordinates here, r, theta, and phi. Because if you have r, theta, and phi instead of x, y, and z, then you have factors of r here, and a sine theta there. Okay? We won't do that. We'll just do everything in x, y, z, unless we absolutely have to. Okay? If you need the determinant of the metric, can anybody tell me the determinant of the metric?
-1.
Can anybody tell me the determinant of the metric?
-1.
Can anybody tell me the determinant of the metric correctly?
It's -1, the determinant is -1.
I'm going to pick a card. Chance. Come on, man. You can do it. You can do it.
What was the question?
Well, before I get the answer from you, I want you to think.
I'm going to say it's 4.
4, yes, exactly. God, you're good. Excellent.
I think
Because this is the definition of the trace of a matrix, of a tensor.
Oh, but it's not the determinant.
Did I say the determinant?
Yes.
Oh, shit.
That's why I was like struggling.
Oh my God, I'm so sorry, man. All right, yeah. Oh my God. Okay, yeah, you have to. Yeah, I'm sorry. Woo! Oh man. Maybe I wrote it as determinant. Nope. I just wrote this, and I'm like, yeah, that's the trace, and I said determinant. God Almighty, damn the brain cancer. Okay, anyway, yeah.
Brain cancer.
Oh yeah, I know. Okay, sorry. Yeah, the trace of the metric is 4. Yes, the determinant is -1. Congratulations, you're all right. And I am the one who is sadly wrong. Okay, anyway, I'm just gonna press on. Screw you guys. So one quick thing to mention is the following. Now you notice if I hit v vector with g mu nu, I get v lower vector. Okay. Now you might wonder, what if you hit v vector with h mu nu, where h mu nu is some arbitrary 0-2 tensor? Does that create a dual vector? What do you think? Who says yes?
I'm not exactly clear.
Who says no? A lot of you didn't vote. This is not a trace. It's not a determinant. This one's straightforward. Yes?
I was going to say, it does form a dual vector, but it doesn't form v mu.
Yes, it does form a dual vector. Look, these nu's disappear, so you're left with a lower mu. So it forms a dual vector, but we would not label that as v. We would give it a new name, like x. It's only the metric which carries us from a vector v mu to its unique dual, v lower mu. Okay? So you just got to be careful. If you're just paying attention to the indices and you don't realize that this is a metric and this is just a tensor, you might change the label here, which you shouldn't, or you might keep the label the same, which you shouldn't. Okay? All right, and then last but not least, are transformations. And this is where people's notation really gets screwed up. But when you're talking about transformations, folks, transformations have 2 indices always, one up, one down, one primed, one unprimed. Always, period. Don't ever hand me any of that other shit. Okay? One is unprimed and one is primed because you're moving from one coordinate system S into another coordinate system S prime. Okay? So this will have T, X, Y, Z, and this will have T prime, X prime, Y prime, Z prime. Okay? It will always have 2 indices because the transformations act on a vector index at a time and a dual vector index at a time. If you've got more than one dual vector indices, you just put a lambda for each of them. You're just putting a lambda in for every index. So the lambdas only have to have 2 indices. Okay? And then sometimes, sometimes we need to know, for example, what this guy looks like. That's the guy that we use to transform the dual vector, and this guy actually looks like the following. He is lambda mu prime mu transpose, inverse transpose. So if you have this transformation matrix, and you want to know this transformation matrix, you take its inverse and then you transpose it. What does it look like if you want to transform a transformation matrix? What does that look like? If you want to transform a transformation matrix, don't do it. That's my lesson. Don't do it. Okay? You transform tensors. You transform the metric if you want, but you use these transformations to do those transformations. Okay, so if we write down a Lagrangian, we're not going to have one of these hanging out in there. We write down the Lagrangian in the form of tensors, and then if we want to transform the Lagrangian, we use these operators to act on all the tensor indices. Okay. Any questions? Again, I know there's a lot that I'm throwing at you, but working with it is what will really make it come home. And honestly, you're going to regret that we leave this when we do, because you'll be like, I want indices back. Why are we doing this? But that's the convention. So, and by the way, the convention that some folks will use, in fact, someone used this in an example after class last week. They came up and they said, oh, well, what if I'm transferring from the mu coordinates to the new coordinates? So they wrote a lambda like that. I'm like, which one's prime? He wouldn't prime one of them. He was like, this is your old coordinates. I'm like, no, you got to prime the damn thing. Okay, so that's the notation that I use and I will use going forward, is that it's always one primed and one unprimed. That's the transition between the two coordinate systems you're using. Okay, so, goodness. You guys are so quiet. You make me nervous. Doesn't anybody have any jokes to tell?
You told us to be quiet.
Oh, did I? Yeah, shut it. Shut the pile. Okay. So, a little bit on index notation and matrices, because it turns out that you can use matrices to represent most of the tensors we'll use in this class, and you can use a lot of matrices to do tensors in GR as well. But you've got to really kind of be careful of how to get things into matrix correct form, and then what to do if you can't use a matrix expression. So I'm going to go back to a really basic example. Okay? Let's go to 2D. Let's bang this thing out. So a position vector in 2D, a differential position vector, would just have two components, dx and dy. Okay? And then we might have a transformation that uses a normal 2x2 transformation matrix, rotation matrix, sorry, cosine theta minus sine theta cosine theta, that acts on the dx dy and gives me, and now we can multiply this bad boy out, cosine theta dx plus sine theta dy minus sine theta dx plus cosine theta dy. And this is what we would identify as our new dx prime dy prime. Okay? Nice. Full gory detail. We good? Okay. Or you could say the following. Lambda mu prime mu. This is the matrix, or the operator that I would attach to this to do the coordinate transformation. So let's actually write down what lambda mu prime mu is. First of all, when you're working with indices, the index on the left you can identify as the row index, and the index on the right you can identify as the column index. A lot of books will write tensors with two indices just like that. Bastards, I know. I always put one to the left and one to the right so you know which one to identify with the row and which one to identify with the column. So that's my row index, that's my column index, and of course, if I wrote this thing down, it would look exactly like this. It's exactly the thing that I used up there, but I want to do it a little bit differently. I want to actually do the transformation of this guy using index notation instead of matrix multiplication, okay? So the first thing we have to do is we have to identify all the pieces of this. So lambda 1 prime 1 is, Joel?
Cosine of theta.
It's cosine of theta. Excellent. I'm going to give you two of them. What is then lambda 1 prime 2?
That would be sine of theta.
It's sine of theta. Jack. What is lambda 1 or 2 prime 1?
Negative sine theta.
And what is lambda 2 prime 2?
Cosine theta.
Okay. Okay. We're just saying, you know, this is the row one, this is the first row, the first column. That's what we're doing. Okay? So, now let's see how it works out. dx mu goes to dx mu prime, which is equal to lambda mu prime mu dx mu. I'm going to show you how this works out with index notation instead of doing matrix multiplication. Right? First of all, notice mu is summed over. So this is lambda mu prime 1 dx1 plus lambda mu prime 2 dx2. Okay? This is why when you do general relativity, for example, you usually label your coordinates by x0, x1, x2, x3 instead of t, x, y, z. That way things have numerical superscripts. But this is y, and this is just good old x in this example. Okay? Now, dx1 prime is lambda 1 prime 1 dx plus lambda 1 prime 2 dy, and dx2 prime is lambda 2 prime 1 dx plus lambda 2 prime 2 dy. I'm just going along, and everywhere I put whatever number I'm putting in there, I'm putting in there and there. Everybody see it? Well, now you plug those in. We good? Okay, this is the exact same thing we got, just doing matrix multiplication of these bad boys. Okay. That was just a little bit of insight into how index notation works and the fact that matrix multiplication can be written in this way. Now comes the huge insight and the reason we use this damn stuff. Okay? First of all, this clearly makes sense, right? Does this make sense? Well, if I write down the column vector for this and the matrix for that, can you multiply those two things? No. Can't do it. But here's the awesome thing about index notation. If you do it this way, you'll get the same expressions. The most valuable aspect about using index notation is that it doesn't matter what order you write things in terms of, which you all know is completely unlike matrices. Matrices have to be written in the correct order. Okay? Generally, if you have matrix A, matrix B, it is not equal to matrix BA. Okay? In fact, sometimes this order doesn't make any sense. All right? But this index notation allows us to write things in any order. We don't have to worry about the order of things. Okay, so that's power number one. Now we have to back up a little bit, because if I gave you this expression and you wanted to evaluate it with matrices, then you're kind of stuck. Because you're like, well, this is a matrix and I can't multiply it. What the hell do I do? Well, it's actually pretty simple. If you want to take an expression in index notation and you want to bang it into a matrix expression, all you need to do is make sure that your summed indices are immediately adjacent to each other. Well, that means switching the order of these, getting this, and then mu and mu are right next to each other, and now you can plug in matrices and do the multiplication. Okay? Everybody got that? I got it written down words in my notes, but I'm not going to write it down. Forgot what the second most important thing was. Damn. It was so important. It was like quintessential to this entire lesson, and if I can't remember it, we're all just going to go home.
It was so important that you forgot it.
Shoot. Oh, yeah. No, man. It's simple.
Do you not have it like written in your notes?
Look at the board. Okay? This is obviously not going to migrate into a matrix expression anytime soon. But evaluating it with the index notation is fine. Okay? I mean, this will be a 2x2, or it'll be a 4x4 matrix because it's 4 dimensions. Sorry, I'm a string theorist. I'm not really stuck in 4 dimensions. But anyway, this will be a 4x4 dimensional thing because it's only got the mu nu, the lambdas will be summed over. But to actually evaluate it, okay, you have to use the index notation. Okay, so you can manipulate higher dimensional things, obviously, with index notation that you can't do with matrix notation because matrices can't even be used to represent them. Okay. Yes. Okay, two important things before I move on. First of all, the good thing about the metric is that it is symmetric. So you can always flop the indices on the metric at will. If I give you an arbitrary tensor, though, then it's not always the case that if you flip the indices, you get the same thing. If I tell you it's a symmetric tensor, then you can. If I tell you it's an anti-symmetric tensor, then you get a minus sign. Or you can just have a general tensor, in which case you don't know what is there. So, but the metric is symmetric, so we can always flip the indices on it. And then last but not least, I have all the different versions of lambda, all the different places that these things could go, and I have them all written down in terms of transposes and then inverses in the notes, but I'm not going to write them on the board. And the reason for that is because if you want to transform, something like h mu nu lambda, if you want to transform this using matrices, matrix multiplication, then it gets a little tricky because you need like various iterations of the lambdas with the primes and the unprimes in different places, and so. But I have all the examples written in this. Okay. All right. So now we're actually going to get into something, because everything I've been doing so far has been math, thank you. It's been math. Now let's talk about something physical for a bit. Okay, so when you do physics, one of the most important things that you're studying in physics is how things change, right? Don't get me wrong, there are static problems, which are incredibly important in certain contexts, which I do not appreciate at all. But most relevant is that you want to study how things change. And if you want to describe mathematically how things change, you need what kind of operator? You need a derivative. You need a derivative with respect to something. You could be talking about a surface, and you want to talk about its change in shape as you move around, so you might want a derivative with respect to space. But, as Ross suggested, you might want to know about the evolution of a system in time, so you might take the derivative with respect to time. So, we know that in non-relativistic physics, we use the gradient operator, which operates on functions and fields. So, we take the gradient of a scalar and the divergence of a vector. And a time derivative. And the time derivative operates both on fields, like the time derivative of the magnetic field with respect to time, but it also acts on particle-like things like the position vector describing where a particle is, how it changes with time, is given by dr dt. Okay? Now, we would like to move to special relativity, where there is no difference between time and space. Time and space are on the same footing. So it really looks like it's obvious how to do that, right?
But how do you take a time derivative of time?
Well, no, I mean, I'm not there yet. I'm going to get there. Okay? So remember, in relativity, we start in non-relativistic physics where we have time, and then we have spatial coordinates, and this is living in a completely different geometry than this, and then we just unify it all into one 4-dimensional coordinate system. So why don't we take d by dt and del, you know what this is, right? d by dx I hat plus d by dy. Okay. And why don't we just dump it into one 4-component derivative, and we're going to call that d by dx mu, which we shorthand d lower mu. And this is literally just the operator d by c dt, d by dx, d by dy, d by dz. Okay? Now this is an incredibly important operator which we will use extensively in this class because it acts on fields, and we work with fields a lot in this class. All right? If you were going to peg this as a tensor, what kind of tensor would you peg it as? Just yell it out.
0, 1.
It's a 0, 1. It's got one lower index. It's like a dual vector, okay? So this guy is a 0, 1 tensor, or you could call it a dual vector. All right? And that tells you how to transform this if you're doing a coordinate transformation, okay? So if you're doing a coordinate transformation to some new coordinates, then you guys can fill in what you put there, okay? All right? Now, this means that the 4 gradient, which is the derivative of a scalar field phi like that, gives me what kind of tensor?
0, 1 tensor.
Yeah, it gives me a 0, 1 tensor. If you think about it, the derivative transforms tensorially, but the derivative is, I mean, you don't build a Lagrangian and just write that. It's got to be taking the derivative of something. So you want to take the derivative of various things and then ask, what is the resulting thing transform like? So if you take the derivative of a scalar, this doesn't transform, this transforms like a dual vector, so it's a dual vector or a 0, 1 tensor. Okay? If you do the 4 divergence, d mu a mu What does that transform like?
0, 0 tensor.
Yeah, it's a scalar. Okay, just like this creates a scalar. Okay? Now, we're going to encounter that derivative a lot, especially when we're constructing Lagrangians. This derivative we're going to see all over the place. It's well defined in this way. In general relativity, this is a big no-no. But in special relativity, it's perfectly fine. We're not going beyond special relativity, so we'll just stick with that. However, that is not the end of the story. Okay? Because it turns out that in this class, although we deal with fields, we are often using the excitations of fields which are particle-like. And we want to be able to describe the motion and the change in position and so forth of particle-like excitations relativistically. Now, what's important is that if you want to deal with a particle, normally what you do is you set up a coordinate system and then you talk about the particle's position. And so if you take the derivative of the position with respect to time, you've defined the velocity of the particle, and then if you there's a bunch of other things, so you can define the linear momentum to be the mass times the velocity. You can define the energy to be 1/2 mv squared, and you can define the acceleration as the derivative of the velocity. So this position is a function of time. You take the derivative of it and then bang all these things out. And these are all interesting dynamical quantities that we can use to describe the energetics or momentum or motion of a particle. And generalizing these ideas to special relativity is going to be important for us, okay? These are particles, not fields. They're particle-like excitations of fields, but don't worry about that right now. But that derivative that I had just written up on the board is not really useful here, okay? So to generalize naively, we could try the following. First of all, dr, which is x, y, z, well, we could just say we live in 4 dimensions. So dr is going to become dx mu, which is c dt dx dy dz. Okay? So instead of thinking about the particle in 3 spatial dimensions, we think about it in space-time. Okay? And then all we have to do is define, instead of the velocity v, which is dr dt, we can define dx mu dt, and then we can go ahead and we can introduce all these other ideas. Okay? It seems pretty reasonable, right? Everybody's looking at Ross. Ross is shaking his head. There must be something wrong. To turn down your animation. Okay. There's a significant problem with this right here. What is it, Madison?
But Alex, how do you take the derivative of time with respect to time?
It's 1.
Okay.
So what's the problem?
It's like a fraction, so it's 1. So it works out. Yeah, that sounds reasonable to me.
You know what the answer is. What is it, Ross?
The problem is that it's not Lorentz invariant because taking the derivative with respect to one of the coordinates doesn't give you a 4.
Yeah, I'll flesh that out. You got it. You got it. Okay, so here's the question: is this a tensor?
Sure.
What kind of tensor is it?
1, 0.
Yeah, this is a 1-0 tensor. The next question we should ask is this a tensor? And the answer is no. Okay, let's see why it's no. All right. So if I have dx mu dt, and I want to transform it, I've got to transform that index right there, but I also have to transform t. T transforms. When you do a transformation, like if you do a rotation in the zt plane, then t gets all screwed up. Okay? Well, I know what this transformation looks like. Okay, dx mu is a vector, so this part transforms with the matrix. But how does that transform? It transforms like the component of a vector. This is the 0th component of this vector. But that is not with matrix multiplication. Okay? It's not like this guy right here makes me add another lambda to this transformation. Okay? So in the end, remember, how do you define a tensor?
Something that transforms like a tensor.
It's something that transforms like a tensor. This does not transform like a tensor. To transform like a tensor, you just need factors of lambda for every index floating around. This needs a factor of lambda and some peculiar little thing that goes in for this dt prime, which I'm not even going to write. You could figure it out. Okay? But I'm not going to write it. I'm not going to elaborate on this. This shit sucks. It doesn't work. Okay? So we need something that works. So we're going to find something else that parameterizes the path of something as it moves. Now let's think about what time does for us. Time is just this sort of, it's like an internal clock. Of course it's time. But it's just this parameter, and as something moves, time ticks up. In fact, time only moves in one direction. Okay? But as this thing moves, time ticks up. Okay? Time itself is not going to work for us for these specific reasons that it doesn't transform in the right way. So what we need is we need something such that as something moves, this thing increases only, like time does, but it also has to be invariant. Okay? So what we're going to use is the path length. If a particle is moving in 4 dimensions, then it's moving, and I can talk about the distance along its path with which it is moved. And we're going to call that tau. Okay? But just think about it. First of all, if you're tracking the motion of something, and I'm just going to do x, y, and t here. If you're tracking the path of something in space and time, even if it doesn't move in space, does it create a path? Yeah, because it exists in time. So the tau is well defined even if it's sitting dead still. Of course, if it's moving, tau is the length of the path that it's actually tracking in space-time. Okay? By the way, these paths that I'm drawing, you might have heard of these before, they're called world lines. How many of you have heard of world lines? Okay, these are world lines. Okay, so let me show you how to determine this path length. So the way that we're going to do it is we're going to replace d by dt with d by d tau, where tau is defined as the integral of the square root of minus ds squared, where ds squared is minus c squared dt squared plus dx squared plus dy squared plus dz squared. Okay? This should be somewhat familiar, because if we take a coordinate displacement vector and we take the corresponding dual displacement vector, Okay? To get from the vector to the dual vector, we had to hit it with the metric, and that put that minus sign there. And then I just multiply this row vector times this column vector, and that gives me this. And this is invariant. Exactly. Okay? So ds squared is invariant. Why am I using minus ds squared?
Because you want to be positive as you move through time.
Yeah, so remember, you can just sit still so that dx, dy, dz are all 0. But dt will never be non-zero, but that means that this thing is negative, and if I want a positive root, then I put a positive there. Now, this is interesting because could dx, dy, dz be so big that this thing actually ends up being positive? Well, let's look at it. Dx squared plus dy squared plus dz squared is greater than c squared dt squared. That's what would have to happen for this to be positive, right? But if I divide both sides by dt squared, then that's just that. If I take the square root, that corresponds to something moving faster than the speed of light. So actually, this is always guaranteed to be negative for something which is massive. But interestingly, what is it if something is massless?
Zero.
It's 0. That is weird. It is especially weird because when something like a photon moves through space-time, it traces a path. It's just the length of that path is 0. We'll worry about that later. But for now, we're just going to talk about particles. So we're going to talk about the path, the parameter being defined by minus the square root of minus ds squared. And then we just integrate it so that we have the total length up to where we've gotten. Okay. So with this in mind, our new velocity is going to be the 4 velocity c, which is, u super mu, which is c times dx mu d tau. And yeah. Bless you. Okay, and the C just gets this to have the units of meters per second because this thing is unitless. Okay? All right, so this is key. This has got a lot of really interesting, nice features, but it's going to be the basis for all of this. Because all of this started with what is dr dt, and then we multiply the derivative of that times mass and get momentum. We take the dot product of the velocity of itself multiplied by half mass to get energy, and then take the derivative of getting acceleration. So we can do all of these generalizations with this guy, but let's talk about a couple of other things before we move into that. Okay, so let's see if we can figure out what the components of this actually look like in some other notation. So first of all, so if we have, for example, the frame S, and then we have the frame S prime, which is moving, and this is the motion of S prime with respect to S, okay? Then what we can do is we can consider an object just sitting at the origin of S prime for simplicity. So this object is at rest with respect to S prime. What kind of motion will be seen in the frame S of this object?
It'll move however S S prime.
Yeah, it's moving, it's stuck at the origin of S prime. So whatever S prime is doing, this is going to do the same thing. Okay? So this is the motion of object seen by S. Okay? And the reason I say this, so we can call this frame the rest frame, and then this is just the non-rest frame. And the reason I'm saying this is because the transformation between one frame and another is where we have the lambda matrices come in. We transform from one set of coordinates, say unprimed, to the primed coordinates. But that can be associated with describing the motion of something. Because if I'm sitting here watching a ball move by, then I can say there's a rest frame associated with that ball, and then any quantity, defined in terms of the ball's rest frame, I can transition into my frame using the appropriate lambda matrix. Okay? So let's see what is seen of the, okay, let me ask you another question. What's the 4 velocity of this thing in S prime?
0. T.
Say it again.
T.
T?
Or
B.
All right, we'll bang it out. We'll bang it out. Okay. But right now I want to talk about how this is seen in S, and we can shift it to S prime in a minute. So let's just go through all of the components. So U0, what is U0?
C.
So U0 is the time-like component of this. So what is X0?
OC dt.
Okay, remember x mu is C, or dx mu is C dt, dx, dy, dz. So the 0 component of this is ct, so this is c squared, so this is c squared dt d tau. What is the first component, u1?
C dx1.
C dx d tau, C dy d tau, C dz d tau. Okay? Now, let's take these last 3 and break them up a little bit. All I did was I took dx d tau and broke it up into dx dt dt d tau. But there's some niceties that come with this. First of all, now every factor has a dt d tau. Secondly, what the hell is dx dt?
It's V.
It's v sub x. So this is c v sub x times something, c v sub y times something, and c v sub z times something. And then all we have to do is figure out what is dt d tau. Well, remember, d tau was defined that way. It was defined as minus ds squared. So that's why there's a plus there and minus is here. Okay? I want to know dt d tau. Oh, shoot, sorry. Nope, I don't know that. Right, I'm dividing everything by dt squared, but I have dx squared plus dy squared plus dz squared divided by dt squared. That's the speed squared. Okay? Well, now I just flip this over and take the square root to get to dt tau. So what does dt d tau come out to be? gamma over c. Or gamma is, of course, 1 over the square root of 1 minus b squared over c squared. Okay. So now I can take this and plug it in up here. I get c times gamma. Oh, whoops. I get, just gamma. Okay. So it turns out if you want to summarize the form velocity of something, the zero component is just gamma c, and then the spatial components are just gamma times the spatial velocity that that thing is moving with. Gamma times v. Now it's a little bit, but I want to make it clear. The gamma that you see here includes all of the components vx, vy, vz. Because gamma is 1 over the square root of 1 minus v squared over c squared. And v squared includes all of vx, vy, vz, even though these are multiplying only components. Okay. All right. Any questions? Now we're going to take that next step. Oh, yeah.
So that means if it's stationary, its forward velocity is c.
Boom. Thank you. I forgot. Yes. So, u mu at rest is, what'd you say?
c.
Yeah, what's gamma when you're at rest?
1.
It's 1. So gamma is 1. What's your velocity when you're at rest?
0.
0. So it's c. Okay. All right. Yes.
Oh, I was also going to say with the forward velocity, it also whenever you take like the Minkowski inner product, you always are going to get out c squared, I believe.
Yes.
Yeah.
Yeah, I mean, I'm not going to go through that right now because I'm about to derive a different expression that we'll find more useful. But in GR, it actually comes out to be -1 because we don't have that MC in there. But I'm not going to mention that for now. Okay, so we've got velocity. We've got this 4 velocity vector. It's got these components. Okay. Now we can define momentum. We just take the 4 velocity and multiply it by the mass. And this is a class where mass is invariant. The mass is the mass. You don't talk about the relativistic mass and talk about transitioning from one mass value to another. There's just one mass. We'll talk about the mass changing later in the class, but for totally different reasons. Okay? So 4 momentum is just mass times the 4 velocity. So of course the components are pretty straightforward. And of course, P me rest is MC. Okay? That might seem like it ain't got much in it. We just multiplied 4 velocity times mass. Let me show you some of the shit that has in it. Okay? Let's start with a nugget. Just a nugget. And then we'll do something that's actually useful. For v over c, much less than 1, we can take gamma and we can approximate it by 1 plus 1/2 v squared over c squared plus higher order shit. It's the brain cancer. It makes me cuss a lot more. Sorry. Okay, you're
Now
right.
you catch it on to it.
Yeah, there you go. Okay, so, sorry, that's 0. So I'm going to take this guy and I'm just going to expand gamma. Okay? So I get 1 over c mc squared plus 1/2 mv squared plus dot dot dot, and then mv plus dot dot dot. And this is going to equal 1 over c times the relativistic energy and the relativistic spatial momentum. Okay? Literally, all I did was I took this and I plugged it in where you see gamma there and there. Okay? Now, here it's a little confusing, but you'll get comfortable with this as you work through stuff in homework. When I talk about relativistic momentum here, I'm talking about relativistic 3 momentum. That's the x, y, and z components of the momentum. These are the descriptions you would use if you want to talk about the energy and the momentum separately. This is the 4 momentum. The 4 momentum contains energy. Right? It contains energy and momentum. So this is the 4 momentum. This is the spatial momentum. This is the thing that you usually see in equations when you're describing, what something's doing. Let's just pull a nugget out. Nugget, right? Yeah, nugget. What is the rest energy?
It's perhaps MC squared.
Oh, it's mc squared. There you go. Somebody got super fucking famous for that.
Is that how
Okay. Yeah, that's it.
supposed to be?
Huh?
Is that supposed to be?
No.
Yeah, it's an M. I was mad at Einstein. No, yeah, so this is where A equals MC squared comes from. Of course, it's like, people take that as like a bedrock and this and that and the other, and this is a little bit more of a bedrock. This expression and this expression. But anyway, but no, it is interesting though, because, prior to E equals MC squared, we always designated energy and momentum as being associated with motion. But, all we're doing is we're trying to define a tensorial 4 momentum. So we had to parameterize the path, or we had to parameterize the motion by the path, and it just works out that you end up with this contribution to your energy, which is there whether you're moving or not. Okay? Now, of course, this factor only matters if you're looking at physics where things are destroying themselves and creating new things, because the rest energy differences, have to be attributed to conservation of energy. But in non-relativistic physics, if you got an electron, you've always got an electron. It's not going anywhere. So this thing is never contributing to the dynamics. Okay, but now I've got to show you something more useful that comes out of this. Probably going to regret having just erased that, but whatever. Since P mu is a vector, what is P lower mu, P upper mu?
Scalar.
It's a scalar, or an invariant. Okay. P lower mu is the dual to P mu. Notice, we define P upper mu with these things. That's the definition. You can find P lower mu, and it'll just be minus M gamma C MV. You can find P lower mu by applying the metric to this. But this is the starting point. Okay, so whenever you're thinking about this, you got to associate it with an upper index.
There should be a gamma between that M and V, right?
Yes, sorry. Okay, now, in particular, if P mu is invariant, that means that P mu in any frame, and now I'm going to, oh no, they're still up there, awesome, is equal to, ready? P mu. Evaluated in the rest frame, where things are hella easy. Right? Let's just do it. If we do P mu, if you do P mu, then you're going to get minus E squared over C squared plus the spatial momentum squared. Okay? And remember, P mu I'm defining as E relativistic over C P relativistic. And now I'm just going to call this E and P. So this E and this P are the relativistic. I'm just not going to write relativistic notation or relativistic labeling anymore. So E and P are these E's and P's. The 4 momentum you're always going to know because it's always going to have an index, mu. Okay? So this guy ends up being this, which you can kind of see instantly because P mu would be minus E over C P. Boom. Okay? What about the rest frame? What do you get when you do P mu in the rest frame?
M squared C, M squared C to the 4th. Oh, and M squared C squared. M squared C squared. M squared C squared. Minus M squared C.
Thank you. Minus M squared C squared.
Sorry.
That's okay.
I'm a little tired.
That's all right. So if you do the dual of the rest frame, this is the only thing that's in there, but it gets a minus sign. And then you multiply it by the original thing. Okay? Oh, wait a minute. Anybody seen that equation before? Oh yeah, you have.
You probably like
What?
move P squared C squared to the other side.
Well, I can. I mean, I can.
That's the equation. That's the.
Okay, well, anyway. However, keeping this on the left and this on the right kind of reminds you of the root of it. This is evaluated in any frame where E and P are non-zero. This comes from evaluating it in the rest frame. Okay? Now, P mu, well, we're getting close to the end. So we can make observations like P mu less than 0 is for particles which have a mass greater than 0. If it's equal to 0, it's for a particle with a mass equal to 0. And if it's greater than 0, it's for tachyon. These are things moving below the speed of light. These are things moving at the speed of light. And these are things moving faster than the speed of light, although we don't really talk about tachyons. Well, we actually will. We will talk about tachyons, but they're not going to be tachyons. But anyway, more on that later. Sorry. Yeah, so I want to kind of finish up with one comment, and I don't think I'm going to get to this last sheet of stuff, which is fine. Yeah. Okay, so I want to make one more comment because this will be important in your homework. So you all remember from Physics 100, when you first learned about momentum, what was the setting in which you largely applied momentum? Collisions, right? And guess what we're going to study in this class? Collisions. We're going to study collisions. So I'm glad you're laughing, and I'm just going to take it that you think I'm funny. Anyway, so here's the beautiful thing about energy and momentum conservation in collisions. It just takes that simple form. If you have an isolated system, obviously you have to take all your colliding objects as your system. Okay, but if you have all your colliding objects as your system, the initial momentum, and this might be total, because we might be adding up the momentum contributions from many different particles, but the initial momentum is equal to the final momentum. Okay? Now, here is an incredibly powerful observation. And this is all the total, but I'm just going to erase total because I don't want to carry that around. Okay? Is the initial and the final momentum evaluated in the same reference frame?
Yes.
Yeah.
Yeah, if they both have mu's. Okay, can I say this?
We need to put a prime on the first PI mu.
Can if they are the same if their initial and final are the same in the same reference frame, are they the same in two different frames?
Yes.
They are. So I have a particle which is moving. So it's got some momentum in the frame where you're at rest and you're watching it move. And then you talk about its momentum while you're in its rest frame. Do these look the same?
Would it be this?
No. No. Look, folks, they're not the damn same. This is not the same. But I'm about to give you something.
Yeah, that's the same. That's the same.
If I take the magnitude of the form momentum in the initial frame, so p mu contracted with the dual vector p mu, is that the same as p mu prime contracted with p mu prime? Well, what is p mu p mu? It's an invariant. It's got to take the same value in this frame as in this frame, as in the double prime, triple prime, quadruple prime frames. So when you're working out a problem, this is a very powerful thing to remember. Okay? It's not saying that the initial or that the momentum in one frame is the same as the momentum in another frame, but the product of the momentum in its dual is the same as the product of the momentum in its dual in another frame. So that's going to be very useful in the homework. Okay? So I want you to pay attention. Okay, let's pack up. Yeah, I have a few more comments about electric and magnetic fields. But you can read about those in the notes. We're not going to be using those anytime soon, so I'm not going to try and go over them today. I'm going to let you go on time. But there will be a last page of notes, which is going to have this in it. And by the way, there's something really interesting, which I'll leave the camera on to talk about. Some guy, I don't know how he did it, and maybe you guys know this, but some guy typed my lectures.
What?
He has created 2 textbooks, long, detailed, beautiful textbooks, which are my words and my drawings on the board, printed, covering particle physics and general relativity.
Can you sue him?
That seems
Yes.
illegal.
Well, now he sent me an email a long time ago. I think it was when I first got brain cancer. I can't remember. I can't remember, but he sent me an email saying, I get a lot of emails about like my videos and everything, and I don't respond to them because I don't have time. But he sent me an email saying he had done this, and I kind of looked at it. I was like, I didn't really look at it. And then some other guy sent me an email last week, was like, I just want to make sure you know this guy did this. And he reiterated the point, and I looked at it, I was like, holy shit. So I'm going to contact the guy and find out, is it okay if my students use your book as their textbook? No, he's providing it for free, so I can send you his link, but but it's pretty awesome because every single thing I'm going to talk about, and it's basically my verbiage turned into text, is available online. So I'll send you guys his
It's
email.
literally just like word for word, like
Well, no, I don't think it's I think it's him listening to everything I'm saying, typing it all down, making all the diagrams, drawings, the graphs, the matrices, everything.
okay.
And I don't know what, I think he used like the 2017 semester of, I don't know, but the semesters haven't changed that much.
You
But
should like sell that.
anyway, yeah, I don't know. It's pretty interesting. But anyway, all right, I'll see you guys.